Welcome to The Explainer. Today, we're going to look at how the constant push for better and better video game graphics, well, it didn't just give us prettier games. It actually fundamentally changed computer architecture for every single one of us.
All right, so let's get right into it. How in the world did this almost obsessive need for better games lead directly to the super complex technology that powers this? Well, the answer is a pretty amazing story about pixels, power, and a totally new way of thinking about how computers work.
So our story really gets going back in the 80s and 90s. The video game industry was just exploding, but it was also running smack into a huge technical wall.
Yeah, I mean, the industry was seeing absolutely explosive growth. Players were always demanding more, and developers, they were desperate to build these bigger, more realistic, more immersive 3D worlds. The demand was it was off the charts.
But here's the thing. There was a major bottleneck. The processors in every computer back then, the CPUs, they were hitting a wall. See, they were designed to do one thing at a time, but do it really, really fast. The problem was they just weren't built for the insane number of calculations you need to draw a 3D world in real time.
So to break through that wall, engineers had to come up with a completely different approach. It wasn't about making the processor work harder, it was about making it work smarter, by getting a lot of them to work together.
And that solution was something called parallel processing. The basic idea is simple, but it was totally revolutionary. Instead of having one super fast worker doing one big task, why not have a whole army of workers tackling tons of smaller tasks all at the same time?
Okay, but this whole new approach, it came with its own huge challenge, right? I mean, imagine trying to get 8 reporters to write one single story together. You can't just throw more people at a problem and expect it to get solved. You've got to schedule them, you've got to split the work up perfectly, and balance the load so nobody's just sitting around doing nothing. It's a total logistical nightmare.
But for graphics, a really specific, kind of elegant type of parallelism turned out to be the perfect solution. It's called SIMD, and the best way to think about it is like a marching band. You've got the conductor who gives one single command, like step forward, and then dozens, maybe hundreds of musicians all perform that exact same action at the exact same time in perfect sync.
And this really gets at the key difference, right? For a job like rendering graphics, where you're basically doing the same math over and over again on millions of different pixels, SIMD is just crazy efficient. It's way simpler to program for this kind of stuff than its more complicated cousin, MIMD, which is more like having all those reporters each working on their own separate story.
So this new way of thinking, this whole SIMD approach, it wasn't just some idea on a whiteboard. No, it led to a whole new kind of processor, a specialized hero built for one job, handling this massive parallel workload.
And here's the really crucial point, the main takeaway. This whole idea of SIMD wasn't just some neat thing for academics to talk about. It was shoved into mainstream computer architecture for one big commercial reason, and one reason only: to make video games look better. That's it. So as these specialized SMD chips got more and more powerful, they eventually earned their own name, the Graphics Processing Unit, or GPU. And a GPU at its core is just a parallel processing beast. It's a pure SIMD engine, packed with hundreds, now even thousands of tiny cores, all just waiting to follow a single command.
And you know what's wild? The real testbeds for these revolutionary ideas, they weren't in some giant supercomputer or a fancy research lab. Nope. They were in the game consoles that millions and millions of us had sitting right in our living rooms.
Oh yeah, the console makers were all in on this. They started using these things called RISC architectures, which basically made their processors simpler and way more efficient. And this just kicked off an incredible arms race. You had the PlayStation and N64 going with MIPS architecture. Then you had the GameCube and the PS3 using IBM's PowerPC. And of course, handhelds were using ARM. Every single company was betting on a different horse, all trying to win the race for the best graphics.
Okay, let's look at a perfect case study, the original PlayStation. It was an absolutely groundbreaking 3D machine, right? But if you ever played one, you remember that signature look, that visual quirk. The 3D models had textures that looked like they were breathing or warping and wobbling every time you moved the camera. So what was going on there? Why did that happen? Well, it wasn't a bug. It was actually a feature, a side effect of how these early specialized GPUs did their job. And it gives us a perfect look into their limitations.
See, the PlayStation's GPU had this clever little trick to make things run faster. It would take the 3D world and basically flatten it into a bunch of 2D shapes before drawing them on screen. But, and this is the key part, when it did that, it threw away a super important piece of info:
depth, the Z component. Without knowing how far away each corner of a shape was, it had no idea how to properly stretch the texture on top of it to account for perspective, so it just kind of guessed, stretching it in a straight line, and that's what caused that iconic wobbly look.
Meanwhile, over at Nintendo, they were taking a totally different approach with the N64. It had this powerful co-processor called the Reality Signal Processor, or RSP for short.
Okay, and this is where it gets super interesting. Inside the RSP was another dedicated piece of hardware called a vector unit. And that vector unit, that was pure SIMD in action. It was a custom-built chip with one job and one job only: to crunch the complex math needed for 3D graphics, doing it on multiple pieces of data in a single clock cycle. It was a fantastic, real-world example of just how powerful this whole parallel idea was.
All right, so this brings us to the final and honestly the most important part of this whole story. The legacy of all these gaming innovations. You know, the stuff born from wobbly textures and vector units, it now underpins pretty much all of modern high-performance computing.
So if there's one thing to take away from all this, it's this: the fundamental blueprint for everything, from scientific research and AI to massive data analysis, that blueprint was forged in the fires of the console wars. The very same techniques they developed just to draw pixels on a screen more efficiently are now being used to solve some of the biggest computational problems humanity has. I mean, just think about your computer or the phone in your pocket right now. The reason it's so incredibly powerful isn't because it has one single core that's running at lightning speed. No, it's because it has multiple cores. That multi-core CPU, and especially that powerhouse GPU inside, they are the direct descendants of the parallel solutions that were invented specifically to solve graphics problems for gamers.
And that leaves us with a pretty fascinating final thought, doesn't it? This playful, purely commercial quest for better graphics, it didn't just give us better games. It accidentally built the foundation for the entire future of high-performance computing. And it really makes you wonder what huge challenges of tomorrow are being solved right now by the toys of today.